practice problem says, what is the major product of the following reaction sequence? So we have a two-step reaction because there's two arrows. We're starting with an alcohol and we have to figure out what the final product is. So whenever you have a kind of multi-step synthesis problem, I recommend drawing out what the product is after each step. And it doesn't hurt to consider what the mechanism is as well. So let's go ahead and give that a shot. So first things first, when we see that alcohol starting material, the first thing we need to consider is that OH group a good leaving group? And the answer to that is no. So this is a bad leaving group. So we learned that if you have a poor leaving group, you have to convert it into a better one. And that's what our tosyl chloride and pyridine are doing in the second step. So if you want to consider like what is tosyl chloride, it's basically a molecule that will convert our bad leaving group into a better one. So it looks like this. And our pyridine looks like this. Okay, the pyridine is a non-nucleophilic base. And we'll use that kind of in our second step of this first reaction. So the first thing that happens is the leaving group or the oxygen on our soon-to-be leaving group is going to attack. And this is an SN2-like reaction. And what this does is it converts that oxygen into an oxygen with more than one bond. So we're going to make this guy right here. And our oxygen now has a plus charge. This is where the pyridine comes in. The pyridine is going to deprotonate this molecule. We call it a non-nucleophilic base because we're not going to act as a nucleophile at all in the reaction. It's just going to act as a base, and so it'll deprotonate this molecule. And so the product after step number 1 is going to look like this. So we have our new leaving group installed. So we say it has a tosyl group. A lot of times we'll just abbreviate this whole thing as OTS. So you could see it drawn like this, and that's the same thing. So that's our product after step 1, essentially, again, converting the bad leaving group into a good leaving group. Lastly, we have to figure out what happens in step number 2. So to do this, we have to take a look at what our reagents are. We have a sodium cyanide, and it's really important to recognize that the sodium cyanide is a strong nucleophile only. So that means we can cross off elimination as an option. So we're only going to be considering SN1 or SN2 in this last step. DMSO is a polar aprotic solvent, and that will help to facilitate the SN2 reaction. So we have a strong nucleophile that also helps facilitate SN2 in addition to the aprotic solvent. So our last step is an SN2 mechanism. And so the cyanide is going to come in and it's going to displace the OTS. So if we were to draw that in, we'd have our cyanide and it's going to come in from the back. So that's kind of the last key thing to consider in this reaction is that we have a stereospecific final step. So the OTS gets displaced and the cyanide comes in from the back. So we invert the alpha carbon in this reaction. And so our final product is going to be molecule number 3 right here, where the cyanide is dashed back. We will not observe molecule 2 because that would have been if we had like carbocation intermediate, for example. And we can cross off options 1 and 4 because those are both elimination products. So the only product that's possible in this reaction is molecule 3 only. And that's our final product for this 2-step reaction.